Okay. Hello everyone. Um, for today's class, we still continue a little bit about the chapter 12, maybe until 12.5, and this Thursday, I will maybe review a little bit. We can start from chapter 10, 11, and maybe more exercise. And also next Tuesday, we also have the exercise, and next Thursday will be the midterm. Okay. I will announce later in the Moodle. Also, I will attach the last year midterm and also quizzes, but it's a little bit different chapters. The last year. Last year I include 3 chapters, but now only 10, 11. So you can adjust your exercise. Okay. Okay, maybe we can start a little bit and see what we have done from the cross product here. We already done and proof some parts for how to confirm whether the cross product is orthogonal to both factors. Okay, so if you have factor A, factor B, the cross product of A and B will be orthogonal to A and also B. Okay, and you can confirm those theorem and make the dot product and need to be 0. Okay, and then we arrive at this conclusion that we haven't discussed this yet, but we will start now. The cross product, the length of the cross product is the length of A multiplied with the length of B and then sine theta. And theta will be the angle between A and B. Okay. Okay. Now let's start with this theorem and why we need to consider this theorem. Okay. Now before we confirming this formula, let me remind you that if you have, let's say, A is A1, A2, and A3, you can evaluate the length of A, and you can use the square root of A1 squared plus A2 squared plus A3 squared. Okay? Now, the same way, we will do the exact same way like this one with the A cross B. Okay, so I will go to the next page to start the equations. So let's write the A cross B. And we have square root of, I think, a little bit long because we have 3 components, right? The first is A2, B3, and then square. And then plus A2, A3, sorry. Okay. Now we start with this long equation, okay, the length of the cross product. And then we are square all this. to remove the square root. So we have a cross B and then squared. And then let's expand the form. So this will be A2 squared B3 squared minus 2 A2 B3 A3 B2. Or let me make in order to make it more clear. Okay. And then plus. Okay, the second one. A1, A3, B1, B3. And then plus. And then plus. It's a little bit long. Okay, so we have this long chain of the product from the squared form. Okay. Okay. Now what we are going to do is we need to factorize to make it A and then B, and then if we multiply them, we just need to minus with something. Okay. So let's factorize these terms out of the formula, and then also these terms. You can check the multiplications, and then you need to minus the terms with this. Okay. So it's quite tricky and quite long, but trust me, this is the way you are factorize the A, B, and then the A1, B1, A2, B2, A3, B3. Okay. Now from here, we have really clear set of A and B, right? So we can make this A and B as our this is actually our length, right? And squared, right? This is also our length and squared. Now we can write the cross product here, the squared, and then it's equal A squared and then B squared. And then minus the last part is this actually a dot product, right? So if you think A1, B1, A2, B2, A3, B3 is results of A dot B, okay? And then you just squared them. So we are writing the A dot B here with square, okay? Now remember that the A dot B is A and B and then cosine, right? And then let's replace the A dot B with this cosine. So you will have okay. And then last part, we are factorize the a squared and b squared. And this is 1 minus cosine squared. And we get the terms sine from here. And we can square root all this. So we get the results in our theorem with sine. Okay, and we are choosing sine to be positive sine theta because sine theta is positive when theta is between 0 and pi. Okay. Now, what is actually the angle really is? It's the, so if you have a vector, let's say this is A, and then another vector here, and this is B. The theta is here in between of vector A and B. If you look here, this is length of B and then sine theta. So we can also conclude that um, two non-zero vectors, A and B, they both are parallel if and only if A cross B is 0. So the sign should be 0 or pi. So theta 0 or theta is pi. In either case, the sign theta will be 0. So that's why the cross product will be 0. And the A cross B, okay, also we can visualize as a vector that is perpendicular or orthogonal. So perpendicular to both A, to both vectors A and B. And its length, okay, its length is A, B sine theta. And this is actually what we are using in physics phenomenon. This is usually how physicists they define the A cross B. So a vector that is perpendicular to the both vectors A and B. Okay. Now, from this vector here, A, B, if you are looking at the a triangle, this triangle. So if we are imagining this as our triangle, okay, with the base is A, okay, so triangle with base A, and the height is B sine theta, right? So we can also evaluate. So if the triangle, we make two triangle here with the same area, okay, we call this terms or this shape is parallelogram. Okay. So from here also, the area of uh, parallelogram, we can interpret as the length of A, vector A, multiply with the height is length of B and then sine theta, right? And thus, this is also, we can say that this is the A cross B. So A cross B, the length of A cross B, we can visualize the cross product here, its length, as area of parallelogram. So if you are having a vector, and the vectors having the angle between them, you will see double triangle, right? We call this double triangle, the shape is called a parallelogram. The area of parallelogram is actually the length of the A cross B, the cross product, okay? So that's the also important for you. So the length of the cross product is equal to the area of the parallelogram determined by A and B. Okay, now let me draw the space for 3 dimensions. And let me make the basis vectors. So let's say this is K, this is I, this is J. Okay, this is just I think a review. Most of you are, I think, familiar with. But let's say we have I, and then we cross with J. What is it's equal with? So I cross J. So how do you make with your hand? Using your right hand. So this is starting from the I here, and then cross to J. So imagine like this and going up, right? So if you rotate and you'll see from the sides, you will see your hand, and then it's going up. So we say that the I cross J is K, and then J cross K, K cross I. The same way you are looking J, and then it's crossing here, crossing K, it's going outside, right? Going here. It's becoming I. Okay, and then K cross I, same way it's going over there, J. Okay. But then let's try J cross I. What will happen? J, or maybe here, J, and then cross I. It's going down, right? It's not going up. So I cross J is not equal with J cross I. That you need to remember. So this becoming negative K, and then this also becoming negative I, and this also becoming negative J. Okay. So I cross J is not the same as J cross I. And also, if you have I cross and then brackets I cross J, this will be I cross K, right? And this will be negative J. But if you have the brackets here and then cross J, it's become 0 cross J. So it's 0. So it's also different. So it's not commutative. So you cannot replace the brackets, okay? And it will be different in order, right? Okay. Okay, some property of cross product. So if A, B, C, they are vectors, and D are scalar. So we start from A cross B. This is equal with negative B cross A, as we mentioned before. And then if you have the scalar and then cross B, you can factorize the scalar and just focus on the vectors. Or you can replace the scalar okay. And then you also can, so basically it's like a multiplications with some set of orders, okay? So it's similar to regular operations, multiplication operation, but it has some order, okay? And if you have dot product, you can replace them because dot product is scalar results, okay, the scalar result. The number 5 is called the triple product. I will introduce later on. So here we are, the property of cross product. So I think one thing you need to remember for the cross product is every time you are visualizing the vectors, always remember using the right hand. Okay, so to see how the vectors looks. Okay, okay. Now I'm going here. Start with the triple products. maybe we start from confirming that this is true, that this is okay. So we start with the if vectors, all terms we define, and we start from A dot B cross C. So let's just start with the dot product will have A1 multiply and then plus multiply plus multiply, right? So multiply with the cross is B2 C3 minus B3 C2 and plus A2 multiply B3 C1 minus B1 C3. And then A3 B1 C2 minus B2 C1. Yeah. So basically you are multiply all okay, so we have the expansions. We have multiply all now. The next thing is we change the grouping. So change the group to C1, C2, C3. So C1 is A2, B3 minus A3, B2. And then plus C2, C2 positive is A3, B1 minus A1, B3 and C3, A1, B2 okay. Now this is becoming the A cross B and then dot C. Okay. So we confirm that the A dot B cross C is equal A cross B and then dot C. Now we can also write the terms A dot B cross C in terms of the determinant, triple product determinant. So this is A1, A2, A3. Okay. Now, if you want to observe the um, the geometric aspect, okay. So for example, let's say this is B, this is A, and C. And then we have an angle here. And let's say we have B cross C. Let's say B cross C is here. So B and then cross C. Use the your right hand, and your thumbs becoming B cross C. And if we are looking at these three vectors, let me make the 3D space first. So if you see the base, it's the same as the parallelogram. Okay, so the base, okay, base is parallelogram, but the whole shape is called parallelepiped. So the volume, if you see this, the shape here, the volume is base multiplied with height, right? And the height is determined by this. Let me write here h. Okay. So if you see the height, the h, okay, from vector A, and then it has angle, so it's become the length of A and then cosine theta. Now you can write the volume of the whole shape here and write down the base is the B cross C, the area of parallelogram, and then multiply with A and then cos theta. And this volume we can exchange with A dot B cross C. Remember that if you have vector A, vector B, this is the result, right? So you can exchange this cosine becomes the dot product the same way like this. So this becomes the dot product. Okay. So this is called the scalar triple product. And probably will be used in some physics phenomenon. Okay. I think the most obvious for physics phenomenon is the torque, the torsion. So you have some force like that. You have radius. This is the torque, and you will have the torque here, in which the torque is the R cross F. And it has some angle here. Okay. But I will leave the physics to you to see and observe. But I hope the mathematics inside the physics, the vectors, you will understand. Okay, I plan to um, continue until 12.5. Let's see if we can make it to 12.5. Okay. So that's the 12.4, the cross product. Okay. Okay. Any questions here? Okay. Okay. Let's continue to 12.5. This is equations of lines and planes. Okay. Well, before I continue 12.5, in chapter 12, the vectors, actual 12.1 to 12.4 is actually just an intro to vectors, which you are already learned. You have learned before what is vectors, what is the dot product, cross product. The important thing, however, in chapter 12 in our lecture is 12.5 and 6, because 5 is more application to see the lines, the plane, and you will use most of lines and plane in next chapters. Also in the 12.6, you will learn how you combine several conic sections into three dimensions shape. Like for example, you have a cone, a cone, and you combine the cone with the ellipse, how it looks like. Uh, and how we are solving that, and make some graphs through some graphs calculator. That's 12.6. So we start from 12.5, the equation of lines and plane. So we start with lines. Let me just draw the diagram. As long as you can observe what the vectors is, how to define the line and plane, you will be safe for next chapter, at least chapter 13 and 14, because you will be using lines and plane a lot. So let's start with lines. So if I'm taking origin here, um, and make some vector here, let's say this is R, and then vector also here. This is, let's say, R0. And we have point here and also point here, P0 and P. And let's make some line through this 2 point. Okay, that's the line. Well, let's say the P0 is start with the initial point x0, y0, and z0. And the P here is just x, y, z. And we also have another vector that goes into the same direction with the green one. Let's say this is V. So line let's say this is L. Okay, line L is determined when we know like P0 point, the initial point, and its direction. In this case, the direction is the vector v, which is parallel, which is the v is parallel with the L. And then let the P, the x, y, z, the point P, it can be anywhere actually, but let P is an arbitrary point on L. And let the R0 and then R, these two becomes the position vector of P and P0 and P. So the R0 is actually OP0, the vector, and R is OP vector. So if you look at these graphs here, when we are using the triangle R and RO, we will have the terms R is RO plus this angle, the L here. Let's say the angle from this green one is A. From P0 to P is A. Well, let's say A. So R is RO plus A. Okay. And let's make the arrow here. Okay. So vector R is equal R0 plus A. Okay. And since A is parallel with V, there is a parameter T such that A will be equal with some T multiplied by V. Okay, and T is a scalar. Okay, see, T is a scalar. So it is a parametric. Okay. So it's become a parametric equations in which we can write down and change A with T and V. So we call this vector equation of L or line. And each T gives a position vector R of a point on L. So in other words, if you are observing this vector, okay, and you are trying to observe the T, let's say you are consider T from -2, -1, 0, 1, 2, you will see from the picture here that your R here, it can be traced from here, going here up until some point in this L. Okay. So if you change the T, okay, let me write again here. That is R is RO plus T V. Okay. So if you change the value of t, you can trace your vector positions on the line L, the green line. Okay. Okay. To give some explanations, okay, if R is on the left side of R0, then the t is negative, right? See, from if you change the t with 0, it will be R equal R0, right? So it's like you are changing your R depends on the line L, okay? Okay, I hope you get it. And then, let me write here. If the vector v we can write as A, B, and C. Okay. The component of vector v is A, B, C. We can write the TV in terms of TA, TB, and TC. And as you see from the picture, R is X, Y, Z, and R0 is X0, Y0, and Z0. And if you are looking at the equation here, then we can make it, we can break down all this plus TA okay. And we have now uh, three scalar equations. The parametric equations, x equal x0 plus at, and then y is y0 plus bt, and z is z0 plus ct. So this is our parametric equations. Parametric equations of line L. Okay. And through, let me write completely, through P0, which is X0, Y0, and parallel to vector P. Okay, so this is the parametric equation. Okay, and the vector V, it's also called the direction numbers. The A, B, C is called the direction numbers. And then we can try to solve this x, y, z in terms of t. Okay, let's start from x. And we have also in y, and also in z. And now we have, because all is the same t, so we can also write this in terms of these equations. This is called the symmetric equations. What is happen if one of A, B, C is 0? Okay. So for example, if A is 0, then we still can use for other terms B and C. And the x is just the same as x0. Okay. Okay. Now maybe some example. Um, so find parametric symmetric equations of the line that pass through the point A and B. And then the second question is, at what point does this line intersect xy plane? Okay, so first you have 2 points, A and B. So these 2 points, we can set up anything. Okay, you can set up A, B, or B, A, the factors. But let's just set up A, B. Okay, let's set up A, B. Let's set up factors A, B. And this will be factor 3 minus 1, minus 1, minus 4. So we have 1, negative 5, and 4. And let the vector AB, let make it our V. Let V is equal vector AB, and it's parallel to line L. So from here, we are observing that this is the direction numbers. and taking okay, and taking the A as our initial point, we can see that our parametric equations will be x is 2 plus 1 multiplied by t. So 2 plus t, or let me write this, is A, and then y is equal 4 plus pt, and z is negative 3 plus c3. And this become okay, this become the parametric equation. So we call this the parametric. And we can set up the symmetric equations. That is our symmetric equations. And then how we find the intersections to the xy plane. So intersect xy plane, if you are seeing the 3 dimensions, so this is the plane, right? So meaning, if you want to intersect this xy plane here, you need to have the z is 0, right? So we need to set up that z is 0, and we have z is negative 3 plus 4t. So negative 3 plus 4t is 0, and we can evaluate t. So at t is equal 3 over 4, line will intersect xy plane. But the question is the point, right? So we need to use the point t is equal 3 over 4 into y and x. So we find x 2 plus 3 over 4, and we find y, and thus this is our point that intersect the xy plane. Okay. Another thing about the vector positions. So let me draw this. So let's say what we have done before is maybe A is here, B is here. Let's say that's the line, and maybe this is the V is here. So let's say we have this AB, vector AB. Usually, um, sometimes we need to make out this vector AB not in a whole line. So maybe we can make maybe only like this little bit here, but it's on the line AB. Okay, so to make out of the line, or we say the line segments. So the line segment. Okay, so for example, if we put t equals 0, we will get back to A, in which if we are looking at the previous question, it's 2, 4, and -3. And if we put t equal 1, it will going back to B, right? In 3, -1, and 1. Okay. So to make this more interesting, we can make this in terms of R with parametric T, and we write this for and -3 plus 40. And let's say the T is from 0 to 1. So we can make out this this kind of equations to see the general equations in terms of a parametric T if we are looking at T from T0 to 1. Okay. So in general, if R is R0 plus TV, and V is R1 minus R0, so we can make this in terms of R1 minus R0 and multiply by T. Or this is called the line segments from R0 to R1 by the interval of 0 to 1. So these terms or these equations is it's actually the same equations as we are mentioned before. It's the same R equal R0 plus TV, but in more general approach, we are cutting the line into some segments. And if we are evaluating from 0 to 1, we can make this in terms of 1 minus t. Okay, so we can observe from sum of t in between of 0 and 1. Okay, that's a more general approach, and that's all for lines. Okay, I'm planning to continue to plane, but because I forgot to bring my laptop charger, but I think it's enough. It's still 35%, so I think enough for until the end, of course. So let's continue a little bit to plane. Any questions from here? Okay, the important thing in lines is making the parametric equations throughout the line and symmetric equations. That's the, I think, important. At least you know the terms. The first term is the parametric. The second one is the symmetric equation. And the rest of the case is you need to imagine the line from here. Okay? So you have the vector position, the initial position here, and then the vector position R in which you need to check or to observe. Okay, and you have also the vectors that parallel to the line. We call the V, in which inside this vector the components are A, B, C, and we call the A, B, C with the name of direction numbers. So this V is the purpose is to become the direction of the vector L here. Okay. Okay, let's go to plane. So what is plane? Uh, what is the definition of plane? Let me make the 3D space. Okay, so first, um, to define a plane, we have defined the line, right? In terms of vector. So we have P and P0. And if you have uh, positions, P position, wait, it's wrong. Okay, if this is a vector, let's say this is A, we know it's line because we have different in its positions, right? So planes is determined first if you have, of course, a lot of lines, so a lot of points that you can connect. Okay, so if you have a connect every point and connecting, and it will become a plane. But how a plane is a plane? Okay, if you have like a random positions, maybe you will have like 3 dimensions, right? So to make it a plane, first let's make out the let's just make the plane here. Okay, let's say that is our plane. And let me use different color. From the origin, let's so it's above this xy plane. So let's make this is our R, and maybe R0 is here. And this is P. So our R and R0 is touching the plane, okay? The vectors touching the plane. So let's make P and P0. So let's say it's X, Y, Z, and this X0, Y0, and Y0. And let's say this is or maybe I will use the just line. Okay. That's the vector PP0. And this vector and we have some n here, a vector n. And let me write, usually the n is for normal vector. Okay, now the plane is determined by P0 and vector n that is orthogonal to plane. And it's called the normal vector. And see that the P0P this is R mean R0. So what does it mean is we can define a plane if we have a normal vector that is orthogonal to every point on the plane. Okay, to every single point of a plane, it's orthogonal. So if we are letting the position factor R0 R and it's making R minus R0, then the normal vector is also orthogonal to this vector. Okay, so the vector n is orthogonal to every vector in plane. So, and in particular, n is orthogonal to R minus R0. And we can have the definitions become this. The dot product of n and R minus R0 is 0. And we can also write down that this is equal with this. So this is called the vector equations of plane. So if we have n with component A, B, C, and R with x, y, z, and R0 with x0, y0, and z0, then the dot product of A, B, C dot the x minus x0, y minus y0, and z minus z0. This resulting 0. And we can write down in terms of the results of the dot product. So A multiplied by x minus x0, B multiplied with y minus y0, and C multiplied with C is equal 0. So this is called the scalar equation of the plane. And sometimes, if you are calculating with some constant, some points, you will also get the results is similar to this. This is linear equation in x, y, and z. So linear equation in terms of 3 dimensions. It's called linear equation. Okay, let's try some maybe 1 or 2 example for the plane, and then we can stop the course. So by definition, you can define a plane if you can define its normal vector. So if you have a vector that is orthogonal to every vector on the plane, then you have the definition of the plane. Okay. So the dot product should be 0 from the normal and then the vector on the plane. So if you need to find equation of the plane, then this is the regular equations. So A multiplied by x minus x0 plus B, and so on and so on. And that is the scalar equation of the plane. Okay, let's try some exercise, some example. For example, find equation of the plane that pass through point P and Q and R. So we have 3 points. Now it depends on you which one you want to make a vector. PQ, PR, QR, PQ, that's fine. Or maybe QP, RQ, RP, that's also okay. In my case, let's start with the PQ. Let's say the PQ is A, then PQ is just Q minus P, right? So 2 minus 4, and 4. And let's say we have the other vector, let's say PR. So I will set two vectors that have the same initial point. The initial point is P, okay? So PR is 4, -1, and -2. So because A and B lie on the plane, right? So we have A cross B that is orthogonal to plane, right? So let's find the A cross B, and that is become our normal vector, okay? So normal vector is equal A cross B. And then you can multiply this and find the results. I'm not sure whether you are familiar or not, but this you can actually adding another I here, another J, and then adding 2, and then 4, 4, -1. And then you can multiply this, plus this, and minus this. I'm not sure whether you get this kind of calculation or not when you learn metrics, but this is also correct to find your determinants. So you can multiply I with 4, -4, -2, and plus J for 4, plus K to -1. So this multiply, and then plus. And then the green color, you are subtract, you're minus. So minus 4 for K, minus 1 for I, minus 2 to J. And you combine both. It will be the same thing when you are calculating through what we learned before. We are learning the 3 by 3 matrix, 3 by 3 determinants. It's resulting the same. And I think this one will be more simple to calculate. Okay. I'm not sure, did you get it in your high school maybe? This kind of calculation to find determinant? Same, right? I think most of the places using this to find to quickly find the order 3 determinants. Okay. And you calculate all of this, it's becoming 12i plus 20j plus 14k. So with point P as our initial point, so this is 1, 3, 2, our initial point, and n as normal vector is 12, 20, 14. So our equation of plane, let me write down so that you are remember how. So we are using A is 12 and then x minus 1 plus 20 y minus 3 and then plus 14 z minus 2. And this should be equal to 0. And we simplify all of this. You can check the answer. And this resulting this equation. So this is the equation of the plane. So equation of plane is this. Okay, I think maybe last two example. So another example, find the point at which the line with, now we are given the parametric equations. So with parametric equation, x equal 2 plus 3t, and then y equal minus 4t, z 5 plus t. They are intersect the plane 4x plus 5y minus 2z equal 18. Okay, first, because we have the parametric equation of each component x, y, z, we can substitute this to our plane equations. Okay. So for 2 plus 3t plus 5 negative 4t minus 2 5 plus t equal 18. And you can check the answers and you will find your t is equal negative 2. And you can get x when t negative 2, x will be, so when t equal negative 2, x will be negative 4, y will be 8, and z will be 3. So this is the point of intersection. Okay, some notes here. Let me check. Okay, still have time. So two planes are parallel if their normal vectors are parallel. For example, if you have x plus 2y minus 3z equal 4 and 2x plus 4y minus 6z equal 3, this is parallel because the first one is having similar direction number in which you can relate n1 and n2. So you can check if the planes are parallel if the normal vectors are parallel. Okay. So so if two planes are not parallel, then they intersect in a straight line. an angle between two planes defined as acute angle between their normal vector, between their normal vector. So if we have so this is the normal vector, and this is the other normal vector. Let's say this is n2, this is n1, and you will have angle theta in between. Okay, now that is I think for planes. Maybe later we will have some review and also exercise, but for now I will stop here